Hi, good afternoon. My name is Scato, Eggen, that's Dutch. I'm going to tell you about functional programming. And so, of course, in the title, Dummies means people without a degree in computer science. I myself, I studied physics, so lots of these category theory stuff that you hear about, had totally no knowledge of, and I'm pretty much self-taught. So I'm not a computer science guy, actually. So, but I dove into functional programming, and this is what I discovered. So, of course, the question everybody asks is, what is functional programming? And some people say, oh, it's programming with functions. Nah. So this is not functional programming. But what is functional programming? I think functional programming is complicated. It's the properties of the language. So something can be a functional language or not. But it's also some common practices that functional programmers do. And it's a theoretical framework. And this is very abstract, but what I mean is you've got these concepts and techniques, and they're very central to functional programming. It's not just pure functions. It's more than that. So this is what I'll talk about today, and I'll start with referential transparency. So the definition that is that an expression is referentially transparent if you can replace the expression with its corresponding value without changing the behavior of the program. For example, we have here a main function that calculates the meaning of life. And there's this expression that evaluates to 41 because it's a post increment. So if you change this with its value, this is allowed because it's just an expression statement, then the return value changed. So this program was not referentially transparent, this expression. Instead, if you write it like this, you assign 41, then you assign 41 plus 1 to j, you return j, you can change the expression you see there, which evaluates to 42 with the actual value, and the program will be the same. So here, the expression is referentially transparent. Now that's the only thing you need to know about referentially transparency. What it also means, why it's so important, is because the FP guys, they say, well, it means you can read code, but you don't have to think about state. You just think about the outcome of an expression. You can forget about state, or the way that evaluating an expression can change that state. So less cognitive burden while reading code, cleaner code. But also, this referential transparency, it gives you stuff, and it makes sure you need other stuff. It gives you pure functions and immutability, but then you need immutable data structures and recursion. So pure functions. This function is pure because you can replace a call to this function with the output. And you could write the function another way, and the function itself will still be referentially transparent, will still be pure, but inside you're using mutation. So these plus equals is actually a operator that then returns the total, so it's an expression. But if you would swap out the expression with a value, the program changes. So this is not this function is not immutable. This function is immutable, so it doesn't look very pure because you're doing assignments, but inside the body of the expression, You're not mutating any variables, so so there's a subtle difference there between pure functions, referentially transparent, and immutability. But if you want to do stuff with data, you also need immutable data structures. Just numbers is not enough, so you want to make lists. And to make a list, actually, you just need a pair. So you have values 1 and 2. You can have a pair of 2 values. Of course, you cannot add a third value to the pair later because that would be mutation. That's not allowed. And to make lists with these pairs, you can use the first value in the pair for a value of the list and the second one for the tail. So these are called the head and the tail. And then you can write a function that either returns the first value or the rest. And these functions are called head and tail. And an empty list, you could, in PHP, write it as null. And then the list 1, 2, 3 would look like this. And then you need recursion. But to understand recursion, you must first understand recursion. So let me try to explain. So if we want an average of not just 2 variables, but a list, then you take the sum of the list, you divide by the length of the list, that's the average. And we create a length function, but it has a loop with mutation, and that's not allowed, right? So we have to write another way. And the same goes for the sum function. We cannot write this with a loop. So what we do instead is we use recursion, which means that the function calls itself. So if axis is an empty list, then the length of an empty list is 0, so we just return that. Otherwise, we take 1 and we add it to the length of the rest of the list. And the same goes for sum, except that you take the value that's first in the list, which is the head, you add it to the sum of the entire tail. Now, to see why this works, it's actually quite nice to step through the evaluation of this function. And we do that by taking part of the expression and replacing it with its value, because we can do that because it's referentially transparent, right? So first we fill in the list, and then we take the function. The body of this function had like the division, sum divided by length. So we put that there. Then each of these function calls, we can do the same. And then here we see a head. We know how to calculate that. It's just the first value of the list, right? 1. And the tail is the rest. So we see another tail here, do the same, and then we have 2 function calls. So you see the loop happening. Here's the recursion. Again, we change it with the outcome, and we change the head and the tail. And then we repeat this. So recursion is a sort of repetition. And we repeat, finally, the sum of an empty list and the length of an empty list is 0. Now here are all these plus operators, which is a sort of function. We can replace those with the actual numbers. And then another operator, and we replace that. And we just calculated the average of the numbers 1, 2, 3. And this is called the substitution model of execution. And it's only possible because of the referential transparency. And to do loops, sort of, you need recursion. So let's look at this recursion, because here we have the recursion at the end of the function. But this means that you get a very large stack trace, because every function calls itself. So if your list is 1,000 items big, then your stack trace will be 1,000 items as well. And there's a way around that if we write this function a little more complicated and we pass the start value. So if we have an empty list, then we just return the start value where we should start, apparently. And then we recurse at the last line by passing the tail and as a start value, the head and the start value that we started with. This function does exactly the same thing, but this one can be optimized because as soon as we return the sum call, then there's nothing in between the call to sum and returning this function. So we can throw away the item on the stack, and that looks like just like a loop, like a goto. And this is called tail recursion, and according to some people, it's equal to the meaning of life. So this was part one. Next up, point-free programming. Not pointless, point-free. So in order for me to explain to you what point-free programming is, I first need you to understand these concepts. And it's a lot, but it's all intertwined, so bear with me. Okay. Higher order functions are defined by functions that accept a function as one of its parameters or returns a function. So we had some code in PHP. I will switch to JavaScript, especially ECMAScript 6, because it has a nice fat arrow syntax. And our code will look pretty ugly if we keep continuing PHP. So this is the same sum function. It's not tail recursion, it's a regular recursion. And inside there is a plus. And I want to rewrite that plus as a function. So it's the add function, of course, and a add function has two parameters. But I'm not going to write it this way. I'm going to write it like this. This is called currying. You have two functions, an inner and an outer function, and they both have one parameter. And to calculate the sum of these two values, you first apply the first parameter, then you get a function back, you apply the second parameter. So add of 1 of 2 evaluates to 3. And add of 1 evaluates to a function. So add is actually a higher order function, and applying only one of the parameters of a function is called partial application. So why is this relevant? Well, we can now write this sum function using the add function. And if we look at it this way, and we compare it to a function called fold right, then we can see some similarities. So first, this is the sort of value that you apply for empty elements. So this is your start value. And then this add function corresponds to the f that you pass in. And then we even have the recursion, because fold right of f of z should be apparently the same as sum. So what fold right does is it takes a function to apply, like add, a start value, z, and then takes a list and does a fold. And sum just takes a list and then recurses. So actually, what this shows you is that sum is actually a partial application of the fold right function. We can do the replacement here, and then these will be the same. So this is a little trick, but we can do much more because we also have a map function. It's also very important. it takes a function and then applies the function to each of the elements of a list. We also have a compose function, takes two functions, and then returns a function, a new function that first applies the second one and then applies the first one. I'm not sure this is actually correct. I think F and G should be the other way around. And another funky function called constants. So you pass in some constant, and then what you get back is a function that always returns that constant. It takes a parameter, but it ignores it, just returns x. So let's use these as well. So we'll create a function called ones. So this does a map of constant 1. So constant 1 is a function that always returns 1. And a map of that function will take a list and turn all the elements into ones. And then we have a length function, and that's just the composition of turning stuff into ones and then doing a sum. Now we have three functions that we defined without using a single parameter. And this is called point-free programming. So why point-free programming? I looked it up, and there's a branch of mathematics called topology. It works with spaces composed of points. There's points in a space. Everybody knows that. And functions between those spaces. So a point-free definition of a function is a definition which does not explicitly mention these points. In programming, you call them parameters or values of the space on which the function acts. So that's part 2. Next part, algebraic data types. So why the word algebraic? Well, algebra is rules for manipulating numbers, but there's rules for manipulating types. Some of them are sum and products, and I'll show you some of these rules and what you can do with them. So I stopped using JavaScript now. I'm switching to Haskell because Haskell has the nice type notation. So I'm hoping I'm not scaring you all, but well, actually that was my goal. So an example of a sum type is Boolean. You have two types, true and false, which contain of one element. Now Boolean is the sum of those types, and it contains two elements, true and false. And you can write functions that map from Boolean to Boolean like not. An example of a product type would be a two-dimensional point. So it's called a product because if integer would have 1,000 points and you take two integers and turn them into one value, then a point can have 1,000,000, 1,000 times 1,000 different values. So that's why the name product type is quite fitting, and you could write a function, for example, that translates a point using a distance, which you also write as a point. Then there's type constructors. Type constructors are sort of functions for types. So maybe is a type constructor, and a is a type parameter. And you can use that if you might have a value of type A. So you might have a number, but you might not. And it is actually a sum type, but it's parameterized. So you can have a maybe of int or a maybe of bool. An example of a function would be isNothing, which checks if you have a value or not, and if you don't have a value, it returns true. Oh yeah, and what you can see here is that maybe is called a type constructor, but the word just, that's a value constructor, sorry. So you can take a value 3 and you can type just before it, and then you get just 3, for example. So try to remember that. You can also have, of course, recursive type definitions. So list A is defined in terms of itself. It's actually a product of list A and A. That's cons A list A. That's a product type. And then you add that to nil, which is an empty list. So it's a sum of a product type of itself. And our length function you could write in Haskell like this. So it really has clearly empty list have length 0, otherwise you add 1 to the rest. And that is called pattern matching. You saw it with the translation, and there the point is also the value constructor. So you use the value constructor to deconstruct values of product types on the left-hand side of the function. So you pack them out. It was 1 point, but now it's 2 values. And the other point is now 2 values. Now you have 4 values. You calculate the stuff, and then you pack them into a point again using the value constructor. And that's exactly what you can do with lists as well. And this is, I think, the main reason, the thing that we miss in most non-functional languages is this sort of pattern matching using algebraic data types. So, there's also something they call the Hindley Milner type system. And this is where it gets all arrogant, and like we're functional programmers, we understand this. So I'm like, I'll try to understand as well. Come on. Okay, so it's a type system that allows you to do type inference and lambda calculus in order to derive the most generic type of every expression in a program. Not helpful. Okay, so this type inference, what is it? Well, I wrote a type definition for length. So I said length is a function that turns a list of A into an integer. But I can just comment that out. That's the dash dash. It's a comment in Haskell. And that will mean that the compiler will have to figure out on its own what type length is. But it has no problem with that as long as I behave. If I do an oops in the code, then the compiler will complain and say that it cannot, there is no instance for numchar arising from the literal. And I'm like, what is this? Well, apparently num is a type constructor that says this type is something that you can add. And char between brackets is actually just a char string, so a string, char list, so a string. And it says, so you're having, so there's a string there because you use the double plus, which is string concatenation. So the result of the second line is string. So length is a function that maps to string, and 0 is not a string, even if we make it more generic. Which is not what we meant. It should have been int. So we can tell the compiler that, and then our oops is actually on the right line. So it says, oh, I couldn't match type int with actual type string. So you're making a mistake there on that line. So types are optional, but they're helpful for the compiler error messages and for readability, of course. And even if we put total nonsense in there, then the compiler says, oh, no, I couldn't match int to this function type. There's an error in there, which means a function that turns a list A0 into a int. Note the A0. Because what does this algorithm roughly do? It starts by taking all the code and all the nodes in the code and all expressions and sub-expressions and assigning a type variable to it, both left and right of an equals for definitions. And it just starts at the top and it moves to the next piece of code that imposes a constraint. I'll come to that. Then it unifies these type variables and then it goes back to step 3 until it reaches the bottom. So these constraints could be things like left and right hand side of equals must have the same type. So if those are two type variables, it will unify those, which just means make them the same name or complain if it can't or do something other smart thing. And the result of plus, for example, has the same type as the expressions on either side, which also must be equal, I think. And applying a function with type A0 to type A1 is only valid for a parameter of type A0, of course. And it should always produce a value of type A1. And it can be really smart about it, like somewhere it finds that A0 should be int and A1 should be equal to A0. Then it can also conclude that A1 is equal to int, which is basic logic. And also if you have type constructors like maybe, it's a maybe int. Okay, so if A3 is maybe A4 and A2 is A3, then A4 must be int. It can deduce that sort of thing, usually. And also, the arrow is not that special in type inference. It's just a type constructor. It should do type inference for all types, so why not the arrow? And it's a type constructor because it turns two types into a new type. So, how are you on time? We have time. Okay, so. Of course, there's also one thing that all functional programmers talk about, category theory, and especially monads. And do you know Douglas Crockford? So he said that once you understand monads for yourself, you lose the ability to explain them to others. So in category theory, there are a lot of weird names, like functor, monoid, applicative, monads. And I will not try to explain even monads and the other. I will try to explain functors only, and hope I succeed. And a functor is, actually we saw a functor because maybe is a functor. And in practice, it just means that there's a function FMap for that type. So in Haskell, you've got these type classes, and then you say class functor, where, well, functor should have FMap, and this is the signature. And data maybe, there's like the type declaration that we had first. And then you can explicitly tell Haskell that maybe is a functor by saying instance functor, maybe, where, and then you have to define the FMap function. And for maybe, which is maybe a value, maybe not, maybe nothing, if you try to map, try to map a nothing, then there's nothing to map, so we can just say, it's nothing. If we try to map f, just a, so we have a value, we have a function f, then we just apply f to that value and we get just a value back. So this is a very simple definition. You can do lots of useful stuff with it. But of course, oh yeah, so like, for example, if you have a function that tests if a value is even, then if you try to map, if you do FMap of is even of just 1, well, 1 is not even, so it's false. So it's just false. And if you try to do that with a nothing, then you get nothing back. So in practice, it's pretty simple, but yeah, so in practice, it's pretty simple and it's pretty powerful. Here's also where the point-free programming comes in, because you can also have a function that works on a maybe int called maybe even. So you partially apply the FMap function, and then you can say maybe even just 1, and it says just false. Maybe even nothing, it says nothing. So, but now I will try to explain functors using category theory. And there, I went on Googling on category theory, and there's this website by a guy called Bartosz Milewski, and it's a very good site. It's a lot of reading, but and he doesn't make it simpler than it is. He really tries to explain category theory and not like the watered down variant where you get the intuition. No, like really what is it called and why is it called that way. And but he also says category theory is quite simple, actually. It's easy in its essence because it's about objects and morphisms. And morphisms you can see like arrows, objects. Category theory doesn't care what the objects are. So actually if you go and make drawings, you can draw the objects as piggies and the morphisms as fireworks. It's still the same, which is what he does. And so I'm like, okay, but I still don't get what do people use category theory for? And so there's 2 examples of categories. Group, which is a category with groups for objects, and group homomorphism. And I heard of group theory somewhere in college, something to do with symmetries, but I don't really get it. But there's another group called sets. And this is the category whose objects are sets. And if you think of it, all our types in programming are sets. A number can be either 0, 1, 2, 3, etc. But it has a maximum value, so that's a set. Booleans are sets of true and false. Strings are even sets if you say are lists of characters and characters. Like the character type is a set. So, and then you have functions between those sets. Like for every number, there's a Boolean that says if it's even or not. So that's a mapping from one set to another. And those form the morphism. So the set category is actually pretty useful for programmers. So what is a functor? A functor is a mapping from one category to another. For example, we have a category drawn as a cloud with objects A and B. And you have a functor f that maps that cloud onto another cloud, which also has objects for FA, FB. And the arrows in between, those have must also be mapped to the other category. And an example of this is maybe. So if you have a, for example, int, then maybe maps that to the set maybe int. And if you have a b or Boolean, then maybe maps that to maybe Boolean. And then you have the isEven function, for example, and you apply FMap, and then you get the maybe even function. And also, because it's maths, they're saying, well, these sets, these categories, they have certain properties, which means that these properties, if you map a category to another category, it must still be a valid category. So these properties must still hold. And one of these properties is that every object must have exactly one arrow that points to the object itself. And it's called ID for identity, because if you take a value and you put it into the identity function, you get the exact value back. So if you put all the values of a set into the identity function, you get the exact same set. But then, of course, if you apply maybe, you must still have a maybe identity in the new category. And it must behave the same way. Also, it says that a set is only valid if you can compose the arrows. So if you have an arrow f from A to B and a g from B to C, you must have a function from A to C. Which means that if you map it to another category, there must still be the function that maps from FA to FC. And in practice, this means the following. So here we have the definition of FMap for maybe. And we have the law that says if you apply FMap to ID, it must still be pointing to itself. So it must be the same as ID. For example, if you put in nothing, it must be the same as ID nothing. You can look at the definition for FMap, and it says FMap underscore, as in don't care, nothing. And on the right side it says nothing. So we can replace, again, the left side with nothing. On the right side we can do the same, because we know that the identity function always returns the stuff you put in. So we can replace that with nothing as well. And nothing equals nothing. So this functor law holds for ID and for nothing. But does it hold for a value as well? So if you put just A in, what happens? Well, if we look at the definition, then FMap F just A is just FA. So we substitute F with ID. So the left side turns into just ID A. But if you apply A to ID, you get A. So that's the third step on the left. And on the right, the identity function, we know it returns the same thing, so it's just A. So now we have just A is just A. So the first functor law, that FMap ID must be ID for that functor instance, holds for maybe. Great. Now let's look at the other law that says FMap PQ. So the dot here is the functional composition, which means apply Q and then P. So FMap of P composed with Q must be the same as FMap P composed with FMap Q. Like this. If H is the composition of F and G, then FH must be the composition of FF and FG. Yeah. So if you do that for nothing, it's a lot of noise, but essentially, yes, this holds. And if we do it for just A, then we have to do a lot of work, especially on the right side, where we use the composition. So FMap P composed with FMap Q of just A means that first you apply FMap Q. So that's in the different brackets. And then you look up the definition and it says, oh, that should be just QA. And then you have another FMap that you apply, and you can look up the definition again, and you get just P of Q of A. So do this as a training exercise at home. It really holds, which is a good thing because otherwise maybe it would not be a functor. So category theory is in essence just a lot of math about objects and arrows. And as Christopher Pitt said earlier, monads are just abstract data types, just like functors. And my opinion is these three concepts are, in practice, what you really need to know to do functional programming. So it's not just pure functions, but you really don't need any category theory. So that's it. Thanks.